Okay, in this video we are going to look at some special types of functions. We're going to graph them, and we're also going to discuss domain and range for each of them. So we're going to start out with quadratics. The most basic quadratic, its parent function would be y equals x squared. The graph of this has 1, 1, 2, 4, 3, 9, like this. This is our basic parabola, we call it. Negative 1, 1, negative 2, positive 4 are those coordinates of the points. So what if we get a more complicated formula? What if we get a more complicated function? We have coefficients a, b, and c. So we have a coefficient of the x squared, we might have an x term, we might have a constant at the end. Well, a couple ways to deal with this. This is what we call our standard form. Here's an example of standard form. We can find the vertex. This is an important feature of a quadratic graph, but its vertex can be found using the formula x equals opposite b over 2a. And once we have that x value, we can put that number into our quadratic function, and we can plot our vertex. So let's go ahead and do that here. Let's take this function, let's find the x-coordinate of the vertex. So x equals 4, is opposite of b, over 2 times 1. So we have 4 over 2, which is 2, and then the y-coordinate is going to be 2 squared, which is 4, minus 4 times 2, which is 8, so negative 4 plus 1 is negative 3, so our vertex is 2, negative 3. Now, how can we find another important feature? Well, another important feature would be the y-intercept, and that's simply found by taking x and making it 0, right? Any place on the y-axis has an x-coordinate of 0. So plug in 0, we get this constant at the end as the y-intercept. And the nice thing about a quadratic function is it's always symmetric, and there's a line of symmetry that runs right through the vertex, and that line has the equation x equals 2. So let's see what this looks like if we graph it. There's a coordinate plane. I'm going to plot my vertex 2, negative 3. Right there. I'm going to plot my y-intercept of 0, 1. And there's this line of symmetry right here. So that means this y-intercept that's 2 units away from the axis of symmetry, we can plot a mirror image over here on this side, and we now have 3 points that we can sketch a rough curve for this quadratic through. Okay, cool, great, but there's another way to do it. We could put the quadratic into what's called its vertex form, which is right here. And the vertex is h comma k. Well, how do we go from this guy to that guy? We use a process called completing the square. And to complete the square, our goal is to rewrite this quadratic so that it can have a perfect square trinomial, which lets us factor it into something squared. So here we go. I'm going to rewrite down here. Let's move down a little. So y equals x squared minus 4x plus 1. All right, to complete the square, what we're going to do is we're going to bump this constant over. We're going to make some space. We want to create a perfect square trinomial right here, this quadratic. I want it to be something I can factor into something squared. And what we're going to do to get that is we're going to take b over 2 and square it. That's what we have to be thinking. So what's b here? B is negative 4. We're going to chop that in half and square it to get 4. Now this quadratic function is factorable, and it's factorable into x minus 2 quantity squared. But wait a minute, guys. I just added 4 up here in blue, and that I can't do unless I also don't do it, where I do the opposite of it, or I'm not allowed to just change the value. I can't just add 4. So how do we balance it out? Normally we'd add 4 to both sides, but I could also subtract 4. Now I'm adding 4 and subtracting 4 at the same time, so I'm really doing nothing. All I'm doing is making it look a little different. And now we have y equals x minus 2 quantity squared, and then this part becomes minus 3. So our h here is 2, our k is negative 3, giving us our vertex of 2, negative 3. And I hope you're saying, wait a minute, that is the same thing we got right over there. And you're right, it is, because we're graphing the same function. It's a different way to get the same thing. So what about domain and range? I said we're going to talk about that. Well, domain is the set of all possible inputs for any function, and the range is the set of all possible y values, the set of all possible outputs. So how do I do this? Well, if we have a graph, it's actually remarkably easy. Domain, we're looking at going side to side here on this graph. Is there any x value as we get bigger and bigger and bigger, or smaller and smaller and smaller, or any place in between that we are not allowed to square and add and multiply and put into this quadratic function? You hopefully are saying, no way, we can put them all in there. So our domain, we can say that x is an element of the real numbers. All real numbers is our domain. We could also say this as x is an element of the set from negative infinity to infinity, non-inclusive. Our range, however, is not all real numbers, because as we look at this graph, as we go up forever, the graph goes up forever, but we can't go down forever. We stop. There's a minimum value that we can have. So what is that minimum value that we can have? Well, the minimum value is negative 3. It's the vertex. So our range, we can say, is the set of all y such that y is greater than or equal to negative 3. In interval notation, it's y is an element of negative 3 inclusive to infinity non-inclusive. And the outside bracket and this parenthesis looking bracket mean the same thing. It means we don't include that endpoint. Square roots, another pretty common type of graph. So what's the graph of the parent function look like? Y equals square root x. Well, we can plug some values in real quick. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 would be 2. And the square root of 9 would be 3. And so on like this. Now, notice I don't go negative because we don't square root negative numbers. The square root of a negative number is not real. So this is the graph of y equals square root of x. The domain of this is x is an element of the set 0 to infinity. And the range would be x is an element of the set 0 to infinity also, except it's not x. We have to make sure we use the correct variables here. We're talking about y for the range. This graph goes up forever and to the right forever, but it stops right there. Notice this form here. More complicated. It's got an h and a k. Well, this pseudo vertex over here is h, comma k. The a value would stretch it out vertically. If there was one, it would make it steeper as we come up here. All these points would get doubled or tripled or whatever the a value is, and we'll look more at that later. But how would I graph this? Y equals square root x plus 1. So how's that compared to our parent function over here? Well, we now know that our h comma k, h is negative 1, so is k. So negative 1, negative 3 is where this bad boy starts. And then the progression of the points is going to be the same. They were here. Like that, but now they're going to be shifted back 1 and down 3, just like this vertex was. So this point gets back 1, down 3. Back 1, down 3, this one back 1, down 3, and there we go. There's our new square root graph that's been translated, shifted because of this addition and subtraction. What's the domain? What's the range? Well, the domain is x is an element of the set -1 to infinity. The range is, I'll put this in set builder notation, a set of y's such that y is greater than or equal to -3. Both are acceptable notations. I hope you enjoy them both, but it doesn't really matter as long as you can read them both. You'll see them both. You need to be able to know what to do with them. All right, graph of absolute value. Absolute value, or modulus, means the distance from 0 on a number line, correct? So if we think about the graph of this, go to x equals 1. Well, 1 is 1 unit away. X equals 2, so 2 units away. X equals 3, that's 3 units away. So we have a graph that is linear like this, but when we go to x equals -1, well, that's 1 unit away from 0. When we go to -2, well, that's 2 units away. So we get a linear graph over here, but with a slope that is opposite of this side. This side, the slope is 1. This side, the slope is -1, ladies and gentlemen. Isn't that exciting? And notice we have at 0, 0, a vertex point. It's a nice sharp point. Unlike a quadratic graph, a parabola, this one comes to an actual point, not a rounded off end. We could give this equation as a piecewise function, y equals x when x is greater than 0, or y equals -x when x is less than or equal to 0. That's what this means, and we'll look more at that coming up in just a second. So let's graph this guy right here and compare it to how it looked for these other ones. Real similar. It's got this HK business again. Guess what? It's the same. Only difference is this negative out here in front. So normally we're at 0, 0, but now our vertex is at 1. That's what we're subtracting from the x, comma 4. So 1, 4 would be right there. And now notice here there's a coefficient of 1 technically. This time it's -1. What do you think that's going to do? Well, hopefully you're saying, ooh, it's going to flip it upside down. It's going to reflect it vertically instead of opening upwards like this. Nuh-uh, it's not going to do that anymore. It's going to open downwards like that. And since there's still a 1 in front of this technically, the slopes are going to be +1 on one side and -1 on the other side. The thing to remember with absolute value is it always makes a nice V. The steepness will be determined by a number in front, a coefficient out front of the x and the absolute value. So there is our graph with the vertex of 1, 4. The domain is all real numbers. All absolute value graphs have a domain of all real numbers. The range, however, is not all real numbers. The range is the set of y's such that y is less than or equal to. Well, what is y always less than or equal to? Y is always less than or equal to what this vertex point is. So 4.